Hello YouTube. So a little while ago I did a video on how modelling and idealisation in science challenges scientific realism. What I'm going to do in this video is return to that topic, and this is in some ways going to be an updated version of that earlier video. I think there are slightly better ways to present the ideas and arguments, and this is going to have quite a bit of new material in it. So if you've seen that earlier video, you might still want to watch this. Okay, so first, the fundamental issue here relates to the way in which scientific models promiscuously use idealizations. But what is idealization? Well, essentially this refers to the way in which a model is intentionally designed to deviate from the facts. Scientists frequently build into their models assumptions that they know are false. And it's worth distinguishing two types of ways models can deviate from the facts: abstraction and idealization. So abstraction, in this case, certain properties of a system are simply omitted from the model of the system. The properties are ignored, but they're not misrepresented. If we're studying the orbit of the moon, then a model of the Earth-Moon system may simply ignore the specific types of elements that the two bodies are composed of. So in this case, we're not saying anything false about the composition of the Earth and the moon, we just don't include that information in the model. Or if we model the swing of a pendulum, the model will probably ignore the colour of the pendulum. Again, this doesn't make the model false. Idealization is a bit more problematic. In idealization, some properties of the system are outright misrepresented or altered in the model, or the model attributes to the system properties that it does not have. In our model of the Earth-Moon system, we might assume that the two bodies are subject only to gravitational forces as a result of their masses. And of course we know this to be false because there are also gravitational interactions with the Sun and Jupiter. Or we might model the Earth-Moon system using Newtonian mechanics. This is false because we know there are relativistic effects. This is a case of idealization. We are knowingly describing the world in a way that is false. So I guess it's maybe worth seeing how this plays out in a more specific example. A classic example of idealization is the ideal gas. An ideal gas consists of randomly moving dimensionless molecules where there is no intermolecular attraction or friction between them. The molecules interact only through perfectly elastic collisions, where a collision is perfectly elastic if the total kinetic energy of the two colliding bodies is the same after the collision as before. So none of the kinetic energy is converted into other forms of energy, such as heat or noise. We have laws that describe the behaviour of the ideal gas. The ideal gas law is stated here, where P is pressure, V is volume, N is the amount of gas, R is the gas constant, and T is the temperature. This tells us, for example, that if the temperature and the amount of gas are held constant, then pressure is inversely proportional to volume. So decrease the volume, you increase the pressure, and vice versa. Of course, it's clear that there are a number of outright falsehoods here. No real gas is anything like an ideal gas on the molecular level. The ideal gas is a mere theoretical construct. This idealization is useful, first of all because ideal gases are theoretically simpler than real gases in various ways, and also because under many conditions the observed behaviour of real gases approximates what we would observe if they were ideal gases. So we can treat real gases as if they were ideal gases in many contexts. Now, the ideal gas is one type of idealization, it's one example of idealization. It's applied in many contexts throughout science. When you look at specific scientific models, these will often include a host of other idealizations. For example, consider stellar models. We can't observe the interior of stars, so astronomers use stellar models to understand their internal structure. These models need to predict properties like luminosity, the chemical composition of the photosphere, helioseismological data, neutrino flux, and so on. Many stellar models assume that a star is composed of an ideal gas, so that's one idealization. Other idealizations that may be used in stellar models include the assumption that there is no density gradient throughout the star, though of course we know that density varies throughout the star. The assumption that stars are isolated in space and not subject to any external gravitational forces. Of course, we know that in areas like the galactic centre, stars may be densely packed. The assumption that stars are composed entirely of hydrogen and helium, even though it's known that stars include heavier elements and that relatively minor differences in the proportions of elements can significantly affect the star's evolution. These are just some examples of idealizations that may be used in stellar models, and of course different stellar models will use different idealizations. But all of them will contain at least some idealizations. So that is idealization. What does this have to do with the realism debate? Well, it challenges one of the central argumentative strategies in favour of realism, the inference from success to truth. We've seen that the primary argument for realism is the no miracles argument, which claims that the best explanation for the success of science is that scientific theories are true. There are different ways to spell this out, but I mean, any kind of realism is probably going to rest on some sort of inference from success to truth. Like the feature of science that should make us confident that it achieves truth is its success. I mean, you know, like why is it that we should believe in electrons and not the Homeric gods? Well, it presumably has something to do with the success of the theories that postulate electrons relative to theories that postulate Homeric gods. Now, different realists will appeal to different kinds of success as justifying belief. So perhaps what matters is successful novel prediction, or explanatory success, or manipulative and technological success in the form of building reliable inference instruments, or whatever. Philip Kitcher has specified the success to truth rule for some claim P as follows. P plays a crucial role in a systematic practice of fine-grained prediction and intervention, so P is approximately true. And I mean, as I say, you might want to rephrase that initial premise in terms of whatever sort of success you prefer, but you know, you get the point of how this works. It should be obvious what the problem is. Consider a model that makes successful predictions. And it doesn't matter exactly how the model is successful actually, but for simplicity, let's assume that what's impressive about it is that it makes correct predictions. Now we know, first, that the model contains a host of idealizations, and second, that the idealizations involved in the model play a role in the derivation of the successful predictions. The model is successful precisely because there are falsehoods contained in it. So we can't in general infer from success to truth. Idealization provides innumerable counterexamples to the success to truth rule. And obviously this argument can be applied no matter what type of success the realist takes to be epistemically relevant. Now, to clarify the structure of this argument, it's worth saying, like, obviously we can't infer that a theory known to contain falsehoods is true in general, right? I mean, even the realist will grant that much. Like, obviously the realist isn't saying we should believe, you know, claims that everybody thinks are false. The problem here is with those parts of the theories that are not idealized. So to put it crudely, some claims made by scientific theories are crucial to the success of the theory but known to be false. Other claims are crucial to the success of the theory but are not known to be false, and it's these claims that we can justifiably believe to be true on the basis of the success to truth rule according to the realist. The point of the anti-realist argument is that the claims known to be false undermine the justification for thinking that success allows us to infer the truth of the other claims. Falsehoods play a key role in the success of science, hence, truth is not the best explanation for success, and success is not a guide to truth. So idealization poses a prima facie challenge to the central argument for realism. Now, it seems to me that there are three possible responses to this. First, we might argue that idealizations do not actually play a crucial role in the success of our best models, and this is because idealizations are in some sense eliminable from those models. So actually, idealizations are not successful, and so there's no way in which the success to truth rule would apply to them. Second, we might accept that idealizations play a crucial role in the success of our best models, but argue that these idealizations can be quarantined from the scope of application of the success to truth rule. So it's perhaps, I mean, I'll explain this in more detail later, but this on this view we kind of limit the success to truth rule in certain ways that are designed to not apply, so that it doesn't designed so that it doesn't apply to idealizations anymore. The third option is to deny that the idealizations used in successful theories are false. It's just to say idealizations are not falsehoods. So idealizations are not counterexamples to the success to truth rule. We apply the rule and we come to believe that the idealized claims are true. So, I mean, summarizing this then, we either show that idealizations are not really successful, which is option A, or we show that the success to truth rule does not apply to idealizations, which is option B, or we hold that the rule does apply and that idealizations are true, which is option C. And I think that's basically exhaustive. These are the possible responses to the idealization problem. And in the rest of this video, we will examine what the prospects for these responses are. Let's begin then with the first option, which is probably the most common realist response to idealization. This proceeds by trying to show that idealizations are eliminable. The assumption is that if idealization is eliminable, then it is not essential to success. At least it is not essential to the kind of success that the realist treats as justifying belief. And so, idealizations aren't really successful, and hence the success to truth rule doesn't apply. Two approaches to eliminating idealizations have proven to be fairly popular. First, we can try to eliminate idealizations using robustness reasoning. For a discussion of this, see J. Odenbo's article, True Lies. The basic idea here is that we can analyse the same system using several different models that all share certain core non-idealised assumptions, and then we look for predictions that follow from all of the models. This allows us to be confident that the core assumptions are true because no particular idealisation is essential to the predictive success of the models. As Richard Levins has put it in his article, The Strategy of Model Building in Population Biology, he has a nice sort of slogan for this kind of view: our truth is the intersection of independent lies. The situation can be viewed schematically as follows. M1, M2 and M3 are models of some phenomenon. A is an assumption that is shared by all three models. X, Y and Z are idealizations that are unique to each model. So you see that each model has like different falsehoods, right? X1 is different from X2, which is different from X3. Then P is a confirmed prediction. In this situation, A is robust over M1, M2 and M3. The idea is that since A has been shown to be robust over this set of models, we have discharged the idealizations X, Y and Z. No particular idealization is essential to success because we can vary the idealizations while still achieving the same success, while still deriving the same prediction. So it's like what's really doing the work in these models is the core assumption A, and that assumption is not idealized. Now, there are a few problems with this approach. A practical problem is that scientists very rarely develop models that are robust from all false assumptions. A model will include many falsehoods, and we may make a few other models with different falsehoods, but we will still find that many falsehoods are shared between the models. So we never have the very clean situation depicted above in my little diagram, where we just have a shared core of non-idealized assumptions with all of the falsehoods varying in the different models. To illustrate this, J. Odenbo, in the article True Lies, considers models of ecological succession. Succession occurs when the populations in an ecosystem replace each other over time. Interestingly, there are patterns in successions. If you focus on forests, you'll find that similar forests will undergo similar successional changes, and dissimilar forests will often converge on similar states, so they'll end up following similar successional changes as well. From many different starting points, we end up getting similar processes. This kind of convergence is found in a class of statistical processes known as Markov chains. In a Markov chain, the probability of transition from one state to another depends only on the current state, not on any previous state. And Markov chains can settle into a characteristic pattern, even when they have different starting conditions, just like is seen in the forest. So ecologists started to model forest succession as a kind of Markov chain. The precise details aren't particularly important, but Odenbo considers some of the models developed by the ecologist Henry Horne. In Horne's first model, a forest is treated as a honeycomb of independent cells, where each cell is occupied by one tree and the cell is the size of the mature tree's crown. It's assumed that all the trees in the forest are replaced at the same time. they're all replaced at once. Furthermore, the probability that a particular species of tree will be replaced by another species is determined by the number of saplings in the understory of the current species. For example, in one of the forests that Horn analysed, he looked at grey birch trees. So he put each grey birch in a cell the size of the tree's crown, and then he counted the saplings in the cells. And he found that there were 837 saplings underneath the grey birches. Of these saplings, there were 0 grey birch saplings, 142 red maple saplings, 25 beech saplings, and so on. And then the probability that a grey birch will be replaced by another grey birch can be worked out. We just take it to be 0 out of 837. The probability that a grey birch will be replaced by a red maple is 142 out of 837. The probability that a grey birch will be replaced by a beech is 25 out of 837. So with this model, we can make predictions about how the forest will develop over time, and it does actually provide a fairly good fit to the observed phenomena. Now, obviously, this model contains a huge number of false assumptions about the ecological situation. Horn then developed other models that contained different false assumptions. For example, he created models that don't assume synchronous replacement. These other models gave the trees varied lifespans. Now again, the assumptions here about the lifespans of the trees are false because we don't know the exact lifespans of the trees. But the point is it's a different falsehood. So that means we can do this robustness reasoning. We can supposedly show that the assumption about the lifespan of the tree isn't really important to the model. We have a bunch of models, each assuming different lifespans for the individual trees, and each of them is empirically successful. The empirical success of the models must therefore be dependent on other features, not the lifespan idealization. So this kind of works, but the trouble is that there are various other falsehoods that are not dealt with in this kind of way. For example, the way the probabilities are worked out, the probability that one type of tree will be replaced by another type of tree. These transition probabilities are a very important aspect of the model, but they're clearly idealized. And Horn doesn't develop a model with a different assumption about these. Also, treating the forest as an independent set of cells, ignoring density dependence. In a real forest, the fact that the trees are more dense in some places will have an influence on the probability of the replacement species. That's not considered in any of the models. Plus, there are a host of external influences on the forest that are not considered in any of the models. I mean, the point of this is just to show how difficult it is in practice to use robustness reasoning on all of the falsehoods in a model, just because scientific models tend to have so many false assumptions. In any case, there is perhaps a deeper problem with the robustness approach. Even if it could be done, it's not obvious why it would help the realist. Recall that the idea is that we have a set of different models, each making various different false assumptions, but each sharing certain core non-idealized assumptions. In this situation, we have shown only that a particular falsehood, say x1, is not necessary for success. But it remains the case that some falsehood, one of the set x1, x2, x3, is necessary for success. So we haven't really eliminated idealization. We've eliminated particular idealization, but we haven't eliminated idealization in general, and so it looks like the inference from success to truth is still threatened. There's a big difference between eliminating a particular falsehood and eliminating falsehood. Every one of our models still includes falsehood, and we haven't got to a situation where we can actually completely eliminate falsehood, even if we can eliminate particular falsehoods. Indeed, part of the problem here is that the eliminability of specific idealizations is actually rather trivial, because any specific claim can in principle be eliminated from a model without reducing the model's predictive accuracy, provided you make the right modifications to your auxiliary hypotheses. This is, of course, the lesson of the Duhem-Quine thesis, which I think I talked about in the video on underdetermination, didn't I? So yeah, I mean, as long as you make the right adjustments elsewhere, you can eliminate any claim in principle. And so it immediately follows that any idealization can in principle be eliminated. But if any claim can be eliminated in principle, both the idealized and the non-idealized claims are eliminable in principle. So if the eliminability of idealized claims shows that they're not successful, and hence not counterexamples to the success to truth rule, looks like we're also forced to concede that no claims are successful, and hence we can't believe anything on the basis of the success to truth rule. So, if eliminability alone is not enough, what more is required? I think the best case for the realist is where we can both eliminate the idealizations and also show that in doing this, we make the model closer. So we show that in eliminating the idealizations, and so bringing the model closer to the truth, it also becomes more successful. So the anti-realist challenges the success to truth rule by pointing out that successful theories and models include a variety of idealizations. Falsehoods can be involved in success, so we can't infer from success to truth. The realist might respond here, well, reducing idealization makes the models more successful, in that they provide an increasingly better fit to the observed phenomena. Right? So reducing the idealization, bringing the model closer to the truth, makes the model more successful. And that supports the claim that the more successful a model is, probably it's closer to the truth. As falsehood reduces, success increases. And this is perhaps inductive evidence for the success to truth in inference. Increasing truth increases success, and hence success is an indicator of truth. And this kind of argument is supplied by the second approach to eliminating idealizations. In this approach, we create increasingly less idealized versions of the model, and we show that these less idealized versions are increasingly more successful. This approach is especially plausible in cases where idealizations are used to simplify computation, and there is an expectation that idealizations will be removed so as to increase the predictive accuracy of the model. As a toy example, suppose we are modelling the orbit of Jupiter and we produce the following series of models. M4 takes just Jupiter and the Sun and treats them as point masses and assumes Newtonian mechanics. M5 takes Jupiter, the Sun and Saturn, treats them as point masses and assumes Newtonian mechanics. M6 takes Jupiter, the Sun and Saturn, treats them as point masses and assumes general relativity. With each step here, there is less idealization in that we are bringing the model closer to what we believe the facts to be. What's more, with each step, the model will presumably produce increasingly accurate predictions, as long as it's worked out properly. As you remove the idealizations, as you remove the falsehoods, the model becomes more successful. So this gives us reason to think that truth is connected to empirical success. Because we've shown, by making these models more true, we make them more successful. And so that gives some support to the success to truth rule. However, there are problems with this procedure, and ultimately I think it's not an attractive option for the realist. First, just like the robustness method, the method of removing idealizations faces very severe practical difficulties, and in many cases scientists simply never attempt it. So even though some theories and models have become de-idealized in some ways, more idealizations have been introduced in other areas, and there's not really a trend towards reducing idealization. De-idealization occurs only in special circumstances. Second, more importantly, it simply isn't true that removing idealizations will always make a model or theory more successful. So Colin Rice, in his article Factive Scientific Understanding Without Scientific Representation, discusses the example of models of honeybee foraging behaviour. The details aren't important, but these are what are known as optimality models. So these are models designed to weigh the costs and benefits of different behavioural strategies. Optimality models use a number of idealizations, so they will assume that the honeybee population is infinite, that there's no overlap between different generations, that traits are passed on unchanged from parents to offspring. One of the main motivations for idealizing in this case is that optimality models are designed to find the fittest behavioural strategy, the strategy that would be favoured by natural selection. So forces other than selection have to be removed from the model. Without those idealizations, the model wouldn't function properly, and it wouldn't predict the honeybee's behaviour. Removal of idealization may also reduce predictive success by reducing the model's scope of application. As Richard Levins has argued in the previously mentioned article, when constructing models, there is always a trade-off between accuracy, precision, and generality. Maximising any of these two will impede the other. As we make a model more precise and accurate, it will apply to fewer cases, in which case it would be a bit odd to say that the model is more successful. If you make a model very accurate and very precise, it won't be general. You won't be able to use it to make predictions beyond some specific situations. For example, one way to explain behaviours in animal populations is to use models of evolutionarily stable strategies. An evolutionarily stable strategy is a strategy that, if it were adopted by all members of the population, cannot be invaded by a new mutant strategy. These models are often highly general, highly idealised. On the hawk-dove model, we consider two behavioural strategies. Hawks fight aggressively to gain or defend their resources, and they don't back down until either they're injured or their opponent submits. Doves immediately back down when threatened, and the model shows that dove is never an evolutionary stable strategy, because any population of doves can be invaded by a hawk. If a hawk enters a population of doves, it will always win a competition for resources, and it will never be injured since its competitors will immediately submit. The hawk is therefore fitter than the rest of the population, so the hawk strategy can spread. Now, general models like these can be used to understand conflict and cooperation in many different species. If we were to remove the idealizations and specify the details of a real population of organisms, the model might produce better predictions about that particular population, but it would no longer be used to derive predictions about other populations, so it would be less successful in that respect. Another problem for option A, perhaps the most serious, is that even if we can show that removing idealizations increases success, at best this could only support the inference that if one theory is more successful than another, then it's likely to be closer to the truth than the other. So when a newer, more successful theory replaces an older one, the newer one is probably closer to the truth. But that is only a comparative claim. Even if M2 is closer to the truth than M1, M2 may still be very far from the truth, and we may not be justified in believing any of the propositions of M2. The trouble with option A is that the realist concedes that we have a host of very successful theories and models that involve substantial falsehoods. She merely says that if we eliminate the falsehoods, the theories and models will be more successful. But it's not obvious how that supports a rule that tells us to infer from success to truth. When presented with some successful theory, we could just as well assume that the apparently correct non-idealized parts of it are in fact incorrect, and hence also need to be altered and de-idealized, and with this further de-idealization will come greater predictive success. In other words, the anti-realist might say, well, for all we know, even our best models are extremely unsuccessful relative to the as yet unconceived true models. The as yet unconceived true models will be far, far more successful than any model we currently have. And that kind of anti-realist claim would be perfectly compatible with the behaviour of scientists who do indeed search for alternative theories and models. It seems like the realist who defends option A can only make a comparative claim that our best models are closer to the truth than our earlier models, but it's not really obvious how that supports the inference from success to truth. Okay then, let's turn to the second option, quarantining idealizations. Realists often engage in what I call quarantining. Quarantining occurs when the realist wishes to say that these claims that are crucial to the success of some model M are true, whereas these claims that are crucial to success aren't. When she infers from success to truth, she wants the inference to carry her only to some specific parts of the model. So she tries to quarantine the other parts from the success to truth rule. The idea of this response is that we can show that the success to truth rule applies only to non-idealized claims. So with the stellar model, the realist infers that its description of the overall structure of the radiative and convective zones of the star, well, that's all true, but its claim that the star is composed of an ideal gas, that's not true. The success to truth inference doesn't carry us to that. The realist must find some way of quarantining the idealizations so that this success to truth rule doesn't carry her to the idealizations. And then, since the success to truth rule doesn't carry us to the idealizations in the first place, they can't be counterexamples to the rule. Now, quarantining has been a popular move in the realism debate, and it might be helpful to consider a more common example. One of the standard arguments against realism is the pessimistic induction. As I explained in my video on this argument, this is often understood as a simple induction on past scientific theories. When we examine the history of science, we find a host of theories that were once very successful, but that have now been shown to be false. So we might argue, many past theories were successful, but have been displaced. By induction, we should expect that currently accepted theories will be displaced in the future. Even if we don't endorse this inductive argument, it's clear that the historical record threatens the success to truth rule by providing examples of false but successful theories. And in response to this problem, a variety of more specific forms of realism have been developed which try to identify continuities in historical theory change. So here's a brief list. Structural realism, defended by John Worrell, holds that we should be realist only about the mathematical or structural claims made by theories. Entity realism, defended by Ian Hacking, holds that we should be realist about the unobservable entities described by scientific theories, even if we're anti-realist about the theories overall, when we can build instruments in order to manipulate such entities. Deployment realism, defended by Philip Kitcher, holds that we should be realist only about those specific parts of theories that are involved in deriving novel predictions. So that is predictions of phenomena that would be surprising given our background knowledge. Hence, Kitcher argues that we find that the working posits of past successful theories are retained over time, while the presuppositional posits that are not involved in deriving novel predictions may undergo significant change. Now, all of these responses involve different kinds of quarantining. The structural realist quarantines claims about entities and claims about the underlying natures of things and applies the success to truth rule only to claims about structure. And this does deal well with some possible counterexamples to the success to truth rule. Fresnel's wave theory of light was very successful, yet Fresnel took light to consist of vibrations in an elastic medium known as the ether, a view which is now thought to be wholly mistaken. But Worrell argues that the structural content of Fresnel's theory, his mathematical equations describing reflection and transmission when light passes between different media, all that stuff survives to this day. And as such, we have no real counterexample to the success to truth rule here. So similarly, one way to deal with the idealization problem is to develop a version of the success to truth rule that applies only to non-idealized claims. The problem is nobody has yet come up with a plausible method for this, and it is very questionable whether it can be done. I mean, the first thing to note here is that whether or not any of these previous quarantining strategies successfully rebut the historical argument, they all end up counting idealizations within the acceptable parts of scientific theory. So none of these strategies quarantine idealizations. The structural content of theories is often highly idealized. Mathematical equations may be true only in idealized models, like the ideal gas law. Although we apply that to real gases, that is itself an idealization. Real gases don't behave perfectly in line with it. Ideal gas law holds only in idealized models. As for entity realism, well, idealized entities are often postulated, as in Horn's assumption that all the trees of a forest are replaced simultaneously, or in assumptions in ecological models that particular species have infinite populations or whatever. Finally, idealizations occur in the working posits that are involved in the derivation of successful predictions. As we noted, optimality models of honeybee behavior would not make the predictions they do without the idealizations. Now, there is an easy way to quarantine idealizations, and this is just to say, just to state, okay, the success to truth rule applies only to the non-idealized claims. Why can't we just say that? Well, I mean, the obvious problem with simply asserting this without further argument is that it's an entirely ad hoc move designed to save the rule from a potential refutation. The question is, if idealizations are falsehoods, and if idealizations play a central role in the success of our theories and models, why should we treat success as a guide to truth? Obviously, we would be mistaken to apply the success to truth rule and then come to believe an idealization. So the question then is, why should we trust it elsewhere? Like, what's the relevant difference between idealized and non-idealized claims? The realist needs to explain why exactly idealizations are quarantined. If the realist can just insist without explanation that the success to truth rule doesn't apply to some proposition P every time somebody proposes a proposition that is crucial to success but that is known to be false, then obviously nothing could ever challenge the success to truth rule, even in principle. Okay then, so in order to quarantine some set of claims from the success to truth rule, the realist needs to show that there is some epistemically relevant difference between these claims and other scientific claims. And this difference needs to be identifiable independently of our beliefs about whether or not those claims are true. So consider again structural realism. First, there's a plausible argument that the structural realist has cited a difference that is epistemically relevant, because she claims that structural content survives theory change, whereas claims about entities are eliminated. Structural content is much more stable. So we have an initial justification for applying the success to truth rule only to the structural content. Second, and very importantly, the structural content of theories is identifiable no matter what your prior beliefs are about which parts of the theory, if any, are true. So, I mean, let's say we encounter some new theory T. We know nothing about T. We don't know whether it's supported by the evidence or how it's viewed in the scientific community. Nevertheless, the structural realist can tell you exactly which parts of T the success to truth rule will not apply to. I mean, why is this important? Well, one way to make this clear is to pose this question to the realist, right? How do you know that the propositions you believe are among the propositions to which the success to truth rule actually applies? I mean, the structural realist can answer this by explaining her concept of structure, by analysing theories into their structural and non-structural content, and then by showing that she believes only the structural content. Now, take somebody who responds to the idealization argument in the easy way, by just saying simply that the success to truth rule applies only to non-idealized claims. Well, again, how do you know that the propositions you believe are among the propositions to which the success to truth rule actually applies? How do you know that the apparently non-idealized claims are not false in a similar way as idealizations? The realist needs to cite some important difference between idealized and non-idealized claims beyond just the fact that we have independent reason for believing idealizations to be false. So could there be a more sophisticated quarantining method? Well, there are reasons to be doubtful, and here they are. First, consider why we introduce idealizations into theories and models. The world is far too complex for any system to be understood in its entirety. We have no choice but to simplify the system and its relationship to other systems in a variety of ways. Scientists are incredibly promiscuous in their use of idealizations. They will idealize wherever and in whatever ways get the job done, and where they may have different jobs in mind, making accurate predictions, unifying phenomena, giving causal explanations, or whatever. Unsurprisingly then, we find various different kinds of idealization in the sciences. Michael Weisberg, in his article 3 Kinds of Idealization, distinguishes 3 kinds of idealization. So in Galilean idealization, theories are simplified so as to be made computationally tractable, and there is an expectation that these idealizations can gradually be removed by improving computational abilities or by using theory to construct more specific models. In minimalist idealization, scientists construct models that contain only the central causal factors to the phenomenon being studied. In multiple models idealization, scientists produce a variety of incompatible models of the same system. I mean, this is the kind of thing that we find in robustness analysis as discussed earlier. Many different incompatible models, all with different falsehoods that provide different perspectives on the same target system. So the first problem then is that that there doesn't seem to be much that actually unifies idealizations and the use of idealizations in models. There's just a whole host of different kinds of idealization. A second and perhaps more serious problem is that the form and content of idealized claims is very similar to that of non-idealized claims, in such a way that many claims that are now considered idealizations might have been taken to be non-idealized if science had developed differently. Consider the idealization that is used in stellar models, that stars consist only of 70% hydrogen and 30% helium. This could conceivably have turned out to be true. If the laws of physics had been different, then perhaps conditions in stars would have been such as to destroy heavier elements, and so to ensure that the proportion of hydrogen and helium was 70% hydrogen, 30% helium, and then nothing else. Nothing in the stellar model itself tells us that this is an idealization. We know it's an idealization only as a result of our background knowledge. This is unlike the case of structural content, which can be identified a priori. So I think these 2 points both suggest that we're going to have some difficulty finding a way to divide theories into the claims to which the success to truth rule applies and the claims to which it does not apply, such that idealizations reliably fall into the latter camp. Okay, let's turn to the final strategy for defending the success to truth rule. The realist can try to argue that idealization does not actually involve falsehood. Idealized claims can be true in essentially the same way non-idealized claims are, and idealized models and theories are successful because they are approximately true. So idealizations are no counterexample to the success to truth rule. Basically, in this strategy, the realist argues for realism about idealizations, in addition to realism about the non-idealized content. This strategy is defended by Stathis Silos in his article Living with the Abstract, Realism and Models, and by Michael Schaffer in his book Counterfactuals and Scientific Realism. Now, the obvious question here is, in what sense exactly can idealized claims be true? Well, Schaffer's proposal is that idealizations should be treated as counterfactuals that tell us what would occur if the world were simpler in various ways. So, if stars were composed of ideal gases and were isolated in space, and so on, then they would behave in such and such ways. Idealizations describe possible worlds where certain properties are removed or simplified. Now, this counterfactual view actually does fit quite nicely to at least one class of models, what William Wimsatt calls neutral models. These are models designed to tell us how a system would behave were certain factors absent. And then by analysing the way the actual system deviates from the predictions of this model, we can infer which of these factors obtain and to what extent. So take, for example, the Hardy-Weinberg model. This model describes allele frequencies over time in a population on which no evolutionary forces act. So it assumes an infinite population with no migration, no mutation, no selection, random mating. By examining how allele frequencies in an actual population differ from the predictions of the Hardy-Weinberg model, we can infer the influence of evolutionary factors in that population. It would be rather odd to say that the Hardy-Weinberg model is false, because clearly it doesn't even try to describe an actual population, and biologists take it that the model does accurately describe what would happen under the conditions it specifies. Now, obviously, not all idealizations function exactly like this. But on Schaffer's view, well, actually they kind of do. There is always some comparison of the idealized situation with the actual situation. Scientists use idealizations because they describe possible situations that may be similar in certain relevant respects to actual situations. The ideal gas is a useful idealization because although ideal gases and real gases differ radically at the molecular level, their higher level behaviour, we might say, is similar in certain contexts. So, scientific theories describe relations between possible objects, like a cylinder of ideal gas, and actual objects, like a cylinder of neon gas. When idealized claims play a crucial role in successful theories and models, we should apply the success to truth rule and infer that those claims are literally true, in just the same sense that non-idealized claims are true. The difference is that non-idealized claims describe actual states of affairs, whereas idealizations describe possible states of affairs. Scientific theories and models as a whole, then, describe the behaviour of both actual and possible objects, and also the relations between these objects. So, this view completely undermines the threat of idealization, because it simply applies realism to idealization. Take, for example, the case of multiple models idealization, where scientists use several incompatible models to understand a system. This might initially seem like a pretty hard case for a realist, because it would be logically contradictory to believe that all of these models are true. The only option here seems to be to identify some specific part of the models that realists can identify as being the truth, as in robustness reasoning, where the realist tries to identify shared assumptions. But on Schaffer's counterfactual view, these different models simply describe different possible worlds, and they tell us how the actual system would behave under different counterfactual situations. And so they're not contradictory at all. There would be nothing at all problematic about believing that all of these models are literally true and completely true. Perhaps somewhat ironically, the realist can take some inspiration here from Bas van Frassen's constructive empiricism, the view that science aims to provide theories that are merely empirically adequate, merely true of the observable world. One of the questions for constructive empiricism is how to deal with modality and counterfactual claims. Van Frassen discusses this issue in The Scientific Image. He gives the example of a model of a pendulum that uses a state space to describe the pendulum's trajectory. Many of the trajectories through the state space that are permitted by the laws of physics will not correspond to how the pendulum has ever or will ever actually behave. They're merely possible trajectories. So, we might sort of say, okay, we can specify the relation between the length of the pendulum and the period of the pendulum or something like that. But then some of those possible lengths, well, the pendulum is never actually has that length, right? So that doesn't correspond to how the pendulum has ever or will ever behave, even though it's permitted by the laws of physics and so is described by the model. Anyway, Van Frassen suggests that the constructive empiricist should treat these possible states of affairs as being on par with unobservable entities like electrons. Possibilities and necessities are just another type of entity that are constructed in scientific models designed to save the phenomena. We are not committed to belief in either the unobservable or the non-actual. And of course, the corresponding realist view is just to take a realist attitude to both unobservables and possibilities. But then if idealizations are counterfactuals, they're no threat to the success to truth inference, because they accurately describe possible states of affairs. Now, realism about idealization raises some very serious puzzles, and I'll present two of the most serious. The first puzzle concerns the ontology of the possible states of affairs described in counterfactuals. What exactly does it mean to be a realist about possibilities? Well, if we take counterfactuals at face value, and if we are realists who hold that possible worlds are on par with other entities postulated in the sciences, such as electrons and neutrinos, then we have Lewisian realism about possible worlds, the view that all possible worlds really exist in just the same sense as the actual world. You can check out my video on modal realism for an extended discussion of Lewis's view. But anyway, on this approach, there really exists a world in which stars are composed of ideal gases. This world exists in just the same sense as our world does, and our stellar models correctly describe how the stars in this world behave. Most philosophers find Lewisian realism simply incredible. Schaffer himself is among those who wishes to resist it, and he notes that other options are available for the interpretation of counterfactuals, which broadly speaking fall into two camps. First, we might hold that counterfactuals are made true by possible worlds, so counterfactuals do describe possible worlds, but that these possible worlds are some sort of abstract entity. Second, we might hold that although counterfactuals can be true in some sense, we don't need to believe that possible worlds actually exist. So we try to find an alternative interpretation of modal language that allows us to say that although the counterfactuals are true, the entities described by the counterfactual don't exist. Now, both of these options actually suffer from what is essentially the same problem. So let's take the first option, the view that possible worlds are abstract entities. This approach seems to be favoured by Stathis Psillos, who holds that the entities described in idealizations really do exist, but are abstract. Like there really are ideal gases, it's just that the ideal gas is abstract. On this view then, the success to truth rule commits us both to concrete entities, such as electrons and mitochondria, and also to abstract entities, like ideal gases and infinite populations and frictionless planes and so on. Okay, well, it's easy to see how this fits in with Schaffer's counterfactual account of idealizations. These abstract objects are studied by scientists because they are such that, if they were physically realised, they would have certain properties similar to the properties of concrete objects. The problem with this is that it looks like we could interpret claims about unobservables, such as electrons, in exactly the same kind of way. We could hold, well, electrons exist, but they're abstract, and they are studied by scientists because they are such that, if they were physically realised, they would result in observable phenomena similar to the actual observable phenomena. So it looks like once we allow, you know, ideal gases and so on, they exist but they're abstract, why shouldn't we just say the same about unobservables? And the realist would not presumably want to say this. Now, one response is that this underestimates the resources available to realism. Perhaps we use the success to truth rule to infer that electrons exist, and then we have additional reasons to believe that electrons are concrete entities. So it's true. On the basis of the success to truth rule, we don't, you know, that doesn't allow us to say that there's any real difference between electrons and ideal gases. For all we know, they may well both be abstract. But the point is, there are additional reasons to think that electrons are concrete. So the success to truth rule gives us the conclusion that electrons and ideal gases really exist. And then there are further reasons to think that electrons are concrete. In particular, electrons are thought to have causal powers that are responsible for various phenomena and that we manipulate using instruments. Susan Weinberg, in her paper Confirmation and the Indispensability of Mathematics to Science, suggests that scientific experiments are often designed to discriminate between different causal accounts, and that to believe a scientific theory just is to believe that the entities it postulates have the causal powers it describes. Only concrete entities can enter into causal interactions, so electrons must be concrete. Unfortunately, this response, I think, begs the question. Suppose we apply the success to truth rule and we conclude that electrons exist. But we're agnostic at the moment between two hypotheses, between the hypotheses that electrons are concrete entities, as would be suggested by taking physical theory at face value, and the hypothesis that electrons are abstract, but if they were physically realised, the observable phenomena would be similar to the actual observable phenomena. In this situation, we have no way of inferring that electrons are causally responsible for anything. Obviously, the world behaves as if electrons enter into causal interactions. That's entailed by both hypotheses. So on the latter hypothesis, that electrons are abstract, scientific experiments distinguish between different abstract entities that would have different causal powers if they were physically realised. And I mean, this is exactly what the what we might call the abstractionist realist like Psillos wants to say about idealizations. Abstract objects like ideal gases are useful in models because they are such that if they were physically realised, they would have properties similar to actual objects. For example, if a star composed of an ideal gas were physically realised, it would have observable properties similar to actual stars. I guess to just recapitulate the main point of this objection, the initial problem for the success to truth rule arises because we have a set of propositions that are crucial to the success of our best theories, but that are commonly believed to be false. Option C involves denying this common assumption and holding that actually the propositions are true. On the abstractionist realism under consideration here, the problem re-arises in terms of whether we take some proposition to be about the concrete or the abstract. We have a set of propositions crucial for the success of science, but which describe only abstract entities. So why then assume that non-idealised propositions, like propositions about electrons, describe concrete entities? The anti-realist can grant for the sake of argument that electrons exist, but then suggest that they are merely abstract, just like the idealizations are merely abstract. Now, the same problem pretty much arises with anti-realism about possible worlds as well. The idea here is to find an interpretation of modal language that allows us to say that counterfactuals can be true, and hence idealizations can be true, even though the entities described by counterfactuals don't exist in any sense. There are no possible worlds. But then the anti-realist will respond, why not hold that propositions about unobservables can be true in some sense, even when the entities and structures described in those propositions may not exist. So propositions about electrons can in some sense be true, even though there aren't actually any electrons. So that's one difficulty for option C. I now turn to the second difficulty, the second problem for realism about idealizations. Let's suppose that we try to avoid all of these ontological debates by just taking the perhaps rather radical step of embracing Lewisian realism. Lewisian realism is an incredible view, but there are some things to be said for it. So one thing to be said for it would be that it would actually avoid the problem just outlined previously. So Lewisian realism is at least theoretically simple, because we now just treat possible worlds as having the same ontological status as other entities accepted in the sciences. There's no need to introduce abstract entities or differing interpretations of modal language or anything like that. Unfortunately, it still doesn't solve the problems of the interpretation and justification of counterfactuals. Idealizing counterfactuals often describe possible worlds that in certain respects are radically different from our own world. Ideal gases, frictionless planes, infinite populations. These are things that could not exist in a world anything like our own. Now, to set up the problem with this, it's maybe worth considering the arguments made by some physicists that various physical constants are fine-tuned, in that if their values were ever so slightly different, the universe would be unable to support heavy elements or complex structures. For example, it's sometimes suggested that if there were a slight increase in the strength of the strong nuclear force, the diproton would be much more stable, which would allow hydrogen to fuse into the diproton. This would make hydrogen fusion much more efficient, such that almost all hydrogen in the universe would have fused shortly after the Big Bang. So we see then that changing certain features of the universe in relatively minor ways can have radical consequences. Another way to put this is, if these fine-tuning arguments are right, then in the possible world where the strong nuclear force is ever so slightly greater, while all the other constants are the same, nothing like our universe even exists. But then, how could we possibly know what would occur in a world that contains dimensionless particles or frictionless planes? These things, imagining a world where there are dimensionless particles, that would bring all kinds of unforeseeable consequences. We don't know where to even start in answering such a question. One thing at least seems clear. A world containing dimensionless particles, I mean, even assuming that this is logically possible, which it might not be, but even assuming it's logically possible, that world would have radically different laws of physics to our own. But in that case, we can't apply our laws of physics to our analyses of ideal gases. And that, of course, leaves us with no justification whatsoever for the claim that ideal gases behave in ways that are similar to actual gases in certain conditions. It seems to me that when we consider idealizing counterfactuals, we're engaging more in an act of just imagination. We sort of say, let's hold these properties fixed and let's change these properties, and then let's just ignore these other properties. And there may be very good reasons for doing this, but that's surely not a legitimate way of proceeding if the goal is to be giving a literally true description of an actual, like a really existing possible world. Changing particular properties would necessarily change others in myriad and unforeseeable ways. An ideal gas could not consist of any molecules that actually exist and would not behave in accordance with forces that actually exist, in which case we have no way of determining what would happen in a universe containing an ideal gas. In fact, there's surely no fact of the matter at all what would happen in such a universe in the absence of a detailed specification of the other laws and properties of this ideal gas universe. I mean, it's worth emphasising here that I'm not intending to argue that Lewisian realism, or indeed any other view in modal metaphysics, entails a complete scepticism of counterfactuals. I am happy to grant, for the sake of argument, that there are many everyday counterfactuals that describe other possible worlds and that we're justified in believing as true. So, for example, if my favourite colour were red instead of blue, I would have taken the red cup. Let's sort of, grant for the sake of argument that this is true. This is an everyday counterfactual. There are, however, some significant differences between the justification of counterfactuals like this and the justification of idealising counterfactuals in science. I mean, how do we know that R is true? Well, I might know that the reason I picked up the blue cup was because blue is my favourite colour. So I think, okay, there was a red cup and a blue cup. Blue is my favourite colour. That's what drew me to the blue cup. So, if red were my favourite colour instead, I would have been drawn to the red cup. Similarly, I can actually go back and physically pick up the red cup, so I can demonstrate that there are no obstacles preventing me from reaching the red cup, and indeed that the same was the case when I picked up the blue one. Like when I picked up the blue cup, there were no obstacles preventing me from picking up the blue cup. I can demonstrate all of the similarities between the red cup and the blue cup. I can show that the colour of an object makes no difference to my ability to lift it, and so on. So we have many procedures for showing the truth of a counterfactual like R. Along similar lines, Lewis suggests that everyday modal beliefs are justified by a principle of recombination. We imagine that things in the actual world are rearranged or duplicated or removed. If we know that a particular situation, we know that a particular situation is possible if we can construct it from an actual situation by this method of recombination. Now, obviously, this doesn't solve all the problems of modal epistemology. I mean, there's lots of problems that I'm just skating over here. But the point is, we at least have some idea of how to proceed. We have some idea of where to start when it comes to everyday counterfactuals. No methods like this are available when we are considering how a star would behave if it were composed of an ideal gas. I mean, for one thing, because there are no actual ideal gases we can examine. It is puzzling, then. It is puzzling just how the success of our physics could inform us about a world containing ideal gases, given that this world would have totally different laws of physics. It is puzzling how we could be justified in asserting anything about this world, given that relatively minor changes in the laws of our world would induce a variety of unforeseeable changes. So, those are some of the problems with realism about idealizations. And I guess that pretty much that pretty much completes the discussion of the idealization problem. But before I end, I do want to draw attention to one other rather interesting point. The debate concerning idealizations mirrors debates in philosophy of mathematics concerning the ontology of mathematical entities. One of the most famous arguments for mathematical realism is the Quine-Putnam indispensability argument, and you can go and check out my video on Platonism in philosophy of mathematics for further discussion of this argument. But we can summarise it as follows. So, we ought to believe in the existence of all and only the entities that are indispensable to our best scientific theories. Mathematical entities are indispensable to our best scientific theories, so we ought to believe in the existence of mathematical entities. This is, of course, basically an argument for the success to truth rule. Just substitute idealised entities or idealizations for mathematical entities, and we have exactly the problem that was outlined at the beginning of this video. Our reasons for believing in unobservables like electrons also entail belief in mathematical entities. One way to frame this issue, which brings out the similarity between idealization and mathematics, is as follows. If the success of science commits us to belief in genes, neutrinos and black holes, why does it not also commit us to belief in ideal gases, infinite populations and mathematical entities like numbers? Our best theories imply both acceptable entities, entities like electrons, mitochondria, black holes, the normal physical stuff, and unacceptable entities, ideal gases, infinite populations and other idealizations, and also numbers and sets and mathematical entities. If we accept the success to truth rule, it seems that we're carried to a host of entities that may initially seem unacceptable. We're carried to idealizations and to mathematical entities. And the responses available in the debate about mathematics mirror the responses concerning idealizations. It looks like there are three options. One is to eliminate mathematics. This is not a popular response, but it has been famously defended by Hartree-Field in his book Science Without Numbers. So the claim here is that mathematical entities do not play a crucial role in the success of our best theories because mathematics can actually be eliminated from these theories. Second option is to quarantine mathematics by showing that the success to truth rule does not apply to mathematical claims. This is defended, for example, by Melia in Weaseling Away the Indispensability Argument and by Hunt in Indispensability and the Problem of Compatible Explanations. Or we might embrace mathematical realism with Quine and Putnam. Abstract mathematical entities and structures really exist. So the challenge of idealization is basically the same as the challenge of mathematics. An interesting difference is that in the debate about idealization, the standard assumption is that idealizations are falsehoods, and this is used to challenge scientific realism. Whereas in the debate about mathematics, the status of mathematical entities is considered to be an open question, and scientific realism is used to defend mathematical realism. So, well, I'm not really sure what to take away from that, but I just thought that was an interesting thing to note. And that is all I'm going to talk about today. So thanks for watching. Goodbye.